About this. '46 Laboratory, Assignment 2. If a system, a sample, has sodium ion in it, as verified by flame test, and has ammonium ion in it, as verified by treatment of a small quantity of the sample with a couple of drops of, say, 1 molar sodium hydroxide solution, and over the mix you wave a piece of damp red litmus paper. Hydroxide ions attack ammonium ion in the sample, produce ammonia, which has two important properties. It's a gas, so it floats up from the sample and meets with the damp red litmus paper, and it's a Bronsted base, so it provokes the damp red litmus paper to become blue. The best test you have in the laboratory for the presence or absence of ammonium ion in a sample. And if that test is positive, and the sample contains sodium ion, how can you test for potassium ion? Flame analysis is no good. So you have to treat the sample so as to remove ammonium ion. And then the cobalt nitrite precipitation reaction will be specific for potassium ion. How do you remove ammonium ion from the sample? See this picture? You put some of the sample, which you know contains an ammonium salt. As a known, you did this with some ammonium chloride in the bottom of your crucible. You heated the crucible strongly, and above the crucible you saw smoke develop, didn't you? How long did you heat the sample? And the answer to this question got nothing to do with time. It has to do with observation. You heated the sample until no more smoke was developing above the heated crucible. And if the only substance in the heated crucible was an ammonium salt, after the smoke no longer developed, if you looked in the crucible was now bare. What happened to the ammonium chloride on strong heating? All of this chemistry is discussed in Assignment 2 Laboratory Discussion section. Did you read it? Did you pay attention to it? What happens to the ammonium chloride when you heated it strongly? What did it do? Well, I agree, it volatilizes, but by what chemistry? What chemistry occurred when you heated the ammonium chloride strongly? To what did the ammonium chloride convert? You didn't read it, did you? If only I could be lab instructor for all the sections. We'd have a lot of fun then. Because until you could answer every one of these questions, you would get from me no okays. Because I want you to learn. By strong heating, you force the Bronsted-Lowry acid-base reaction to occur, which under normal lab conditions will not occur. You force transfer of H+ from the weak acid ammonium ion to the very weak base chloride ion. This produces what? Ammonia gas and hydrogen chloride gas. Both of these materials are gases under normal lab conditions. So clearly under the high temperature of this investigation, the ammonia and the HCl remain as gases. They leave the crucible. What happens when the ammonia and the HCl vapors cool off, and as they cool off, they clobber each other, because they're both produced by this reaction. Do they react again? Will ammonia gas react with HCl gas? You're damn right. And on this reaction, what do you make? Ammonium chloride. That's the smoke. It's a solid. Do you not learn in 2045 that smokes are suspensions of solids in vapor? What do you think a smoke is? Smokes aren't transparent to light. They got solid particles suspended within. You didn't learn this? Yay. Now then, what did we do yesterday? Pardon me, Monday. We prepared some silver chloride. We purposely contained it in a rather large volume of deionized water just so you could better see the whole system. And then while I gently swirled, I don't even know if I did that, I added a few squirts of 6 molar ammonia, and before your very eyes, the silver chloride disappeared, didn't it? Why did silver chloride disappear? Because the silver ion in the silver chloride reacted with the ammonia molecules to make the silver ammonia complex ion, a solution species. So the silver chloride dissolved by reacting with ammonia. Product, silver ammonia complex ion and chloride ion. And then I said, at the conclusion of this investigation, let's now treat this system with some 6 molar nitric acid solution. And on so doing, I told you to make 2 observations. Observation number 1, what happens in the liquid part of this system, and what will happen above the liquid part of the system. Well, you all succeeded in recognizing that by clobbering the ammonia molecules, as well as the silver ammonia complex ion with hydronium ion, supplied by the addition of the nitric acid solution, silver chloride would redevelop, which of course it did. So the white curdy precipitate reformed in the liquid part of the system. But above the system you saw smoke, didn't you? And I asked you to tell me the smoke, identify the smoke. No one did that successfully. Can you now do it? What is the smoke which you saw? Remember how we dissolved the silver chloride? We poured 6 molar ammonia into the system, didn't we? Do you think the pouring of the 6 molar ammonia produced a fairly high concentration of ammonia molecules in the vapor phase above the liquid system? In the laboratory, have you had cause to observe the odor of 6 molar ammonia? Would you like to take the bottle off the cap off the 6 molar ammonia bottle in the lab and go, if you do that, you'll only do it once. And plow, you're going to flop down. Because these ammonia molecules, which you will now have inhaled in high concentration, will knock you flat. Ammonium carbonate, a mystical compound. It can't be made. Because ammonium ion and carbonate ion react with each other to a large extent. You ever hear of prize fighter smelling salts? The poor guy's getting whacked all over the place. Do they stop the fight? Hell no. They put the smelling salts under his nose, which is a source of ammonia, and the acrid odor snaps him back so he can go back in there and get some more hell beat out of him. What is this smoke? Because through the ammonia vapor we were pouring nitric acid solution, right? And what are the components of nitric acid solution beside water? Hydronium ion and nitrate ion. What did the hydronium ion do to the ammonia molecules in this vapor? They protonated them, made ammonium ions, didn't they? So what did the ammonium ions look to react with? A negative ion that's in this, also in this vapor. What is that negative ion? What is it? Nitrate ion, right? Didn't we pour the nitric acid solution through the vapor? That's what the smoke is there. It's ammonium nitrate. If you simply observe and think about what you're seeing, you can learn a hell of a lot. I know you know that. And one of the things that chemistry has to try to do is to teach you to make observations carefully. Because you cannot make sound conclusions from an investigation unless you have made the appropriate observations during the investigation. This is the chemistry which took place in the solution part of the system when we added the nitric acid solution. Could you write a reaction equation to show the chemistry which took place in the vapor phase above the solution part, which would now show the formation of ammonium nitrate, be hydronium ion plus ammonia plus nitrate ion, product, ammonium nitrate and water. Bingo. Hardly enough water in this vapor phase to keep the ammonium nitrate dissolved. That's why you saw the smoke. All right, questions 18, 19, 28, and 29, which are a consequence also of the demonstration which we did regarding the formation of silver chloride, followed by the dissolution of silver chloride by treatment with ammonia. The main purpose of which was to get you to realize that both ammonia molecules and chloride ions are strong Lewis bases towards silver ion. Lewis bases. They react favorably with silver ions to make coordinate covalent bonds. But which makes the stronger bonds? Since we dissolve the silver chloride quite readily, most of you, if not all of you, overlooked the gang-up factor and said, aha, the ammonia makes the stronger bonds. Not true. If we had not dissolved all the silver chloride, but only part of it, this equilibrium would have developed. Because this reading left to right is the chemistry which occurs by dissolving silver chloride on treatment with ammonia. K for this reaction we calculated. And as soon as we get this K, which is a good deal smaller than 1, it's already answering the question for us. It's telling us this reaction is not thermodynamically spontaneous under standard state conditions. Oh, that's a mouthful. What does it mean to say a reaction is spontaneous under standard state conditions? Do you remember the discussion from 2045 laboratory assignment 7? Because dirty old Horvath expects that you not only read it, you learned from it.
Spontaneity there for it's like a mole that fully dissolved it?
Well, not quite. We'll get more on that in the next chapter, where we'll drive home the meaning of standard state conditions versus any conditions, because this is very fundamental in understanding what thermodynamic terms mean. So we'll pass by that for now. And just go back to the statement that since K for this is much smaller than 1, it's telling you this reaction does not proceed to a large extent left to right before equilibrium is achieved. Let's take it from that standpoint, because that we've already done with our acid-base chemistry, etc. Now comes the final proof. Question 29 is asking you, imagine making a mixture of 1.0 mole silver chloride with 1.0 liters of 6.0 molar ammonia. Notice that for this reaction to proceed, you've got to have 2 moles of ammonia per mole of silver chloride dissolved because of the composition of the silver-ammonia complex ion. Just for fun, what do you think the structure is of the silver-ammonia complex ion? Structure. We'll get at this kind of stuff in detail in chapter 24. What do you think the structure is of that? Shape. It's a silver ion to which 2 ammonia molecules are coordinated. So it's really a material composed of 3 groups. Silver ion, ammonia molecule, ammonia molecule. Well, only 3 possibilities exist. It's triangular, which would mean 2 ammonia molecules are bonded to each other. You think that's likely? So let's forget triangular, which means it's either a straight line molecule or it's angular. Can't be anything else. What's your bet? That's what I heard. I got a hybridized answer. A hybrid which is no good. It's linear. More on that later. Back to this issue. What will be the composition of this system when it comes to equilibrium? Noticing that in this system, per mole of silver chloride, we got 6 moles of ammonia. So the gang-up factor is clearly in favor of ammonia, isn't it? Well, here's the equilibrium constant. The equilibrium reaction treated algebraically says if we choose to call the solubility of silver chloride in the ammonia solution S, then S will be the equilibrium molarity of the silver ammonia complex ion as well as the equilibrium molarity of the chloride ion. If the original system was simply silver chloride mixed up with ammonia. Okay? So, these are each S. The ammonia molecule concentration in equilibrium was 6.0, what we started with, less 2S, the amount required to establish the equilibrium. So we get this, and we see this is the perfect square, so we'll take the square root of each side, solve it simply, and this gives S of 0.29 molar. So given that we started with 1.0 moles of silver chloride to make this mixture, only 0.29 moles of the silver chloride dissolved. So 0.71 moles of the silver chloride remained intact. So take note of the composition of the system, which contains total moles chloride ion 1.0 and total moles ammonia molecule 6.0. Material balance. Ammonia molecules ganging up on the chloride ions in the ratio of 6 to 1. But chloride ion got most of the silver ion, didn't it? So who makes the stronger bonds? Chloride ion, of course. Now then, a similar consideration. Silver oxide. Anybody yet in assignment 6 in 46L and observed the formation of silver oxide? What silver oxide look like? Brown, black, powdery stuff. Slightly soluble in water like silver chloride. Which material is more stable, silver chloride or silver oxide? Which material is more stable, let's put it this way, more stable in water. It's going to be more stable anyway, but since we're considering dissolving in water, let's refer to water. Which is more stable in water, silver oxide or silver chloride? Silver oxide. Well, at the end of assignment 6, you'll do an experiment. The experiment will show you that if you take a small quantity of silver oxide and next to it a small quantity of silver chloride and treat each with a given quantity, the same given quantity for each treatment of ammonia solution, the silver oxide will dissolve readily and the silver chloride will not. Now would you like to refine your conclusion about which is more stable? Silver chloride or silver oxide? Silver chloride's more stable, a good deal more stable. Upshot, if you take silver oxide and treat it with a source of chloride ion, right before your eyes it'll convert to silver chloride.
So why does silver oxide have a lower solubility?
It does not have a lower solubility. It has a lower solubility product. And if you have not yet recognized that solubility and solubility product are not synonymous terms, you better get at it. And they're not the same. The solubility of silver chloride is lower than that of silver oxide. Now then, as over here we considered silver chloride being treated by ammonia to get the silver chloride to dissolve, let's consider treating silver oxide with ammonia or a potential source of ammonia. First, let's treat with ammonia. Can you write a reaction equation for this? Do it now on your paper. Let's go. Silver oxide treated with ammonia. I'll get you started with this. Because the silver ammonia complex ion is a heck of a lot more stable than silver ion AQ, which you should know, because that's what the Kf value for the silver ammonia complex ion tells you. Because this involves the reaction of silver ion AQ with ammonia to make the silver ammonia complex ion. In this system, what's the fate of oxide ion as silver oxide dissolves? Which means the oxide ion reacted with what? Water. Because in this system, water is the strongest acid present in appreciable molarity. So if you now wish to compare the solubility of silver oxide in ammonia solution to that of silver chloride in ammonia solution, because we got it done here for silver chloride ammonia solution at 0.0029, that's the K value. Then you've got to calculate the K value for this thing. See if we've got a value here someplace. There it is. Well, since we've already reminded you that silver chloride is less soluble, more stable in water than silver ammonia complex ion, how do you think the K value for this reaction will compare to 0.0029? If silver chloride is more stable than silver oxide, will this K value be larger or smaller than 0.0029? There's the K value. You can do the arithmetic. You now know how to do the arithmetic. Now to do this arithmetic, you're going to have to get the KSP for silver oxide. Now the KSP for silver oxide is given to you on our information sheet. You think this reaction corresponds to KSP silver oxide? You better not think that. You think the KSP for silver sulfide corresponds to silver sulfide in equilibrium with silver ions and sulfide ions? Are we going to get a measurable molarity of sulfide ions in water solution? We're going to get a measurable molarity of oxide ions in water solution? No and no. And since this is occurring in water solution, then what we are recognizing (10 to minus 16) is it 3.6? I don't know, that's a number coming to me. Got the information sheet handy, anybody? 3.5, damn it, I missed it by a little bit. I better have another dream about my information sheet. Okay? Now then, in passing, I could at this point remind you, and will at this point remind you, you remember the equilibrium reaction we wrote involving calcium carbonate? The calcium carbonate plus water, double arrows, calcium ion, hydroxide ion, hydrogen carbonate ion. Remember that? You remember that? For which the K value is 1.3 times 10 to minus 12. My question is, can I take 1.3 times 10 to minus 12 also as a KSP for calcium carbonate? Does it not correspond to the equilibrium which is established when calcium carbonate is dissolved in water? Does it? Yes? Then it's also a KSP for calcium carbonate. So what you've now learned is that there's more than one way to write a KSP. but it has to reflect the chemistry which occurs when the stuff in question goes in the solution in the solvent in question. And our solvent in question is always water. How about that? So KSP is not necessarily dissociation equilibrium exclusively, is it? It may also be the equilibrium which reflects the chemistry of the base, the anion component, which is a Bronsted base for the semi-soluble salt. How about that? Now then, if I take and treat silver oxide with ammonium nitrate solution rather than ammonia solution, will I get a bigger K than this or a smaller K than this? If I treat silver oxide with ammonium nitrate solution rather than straight ammonia, will I get a bigger K or a smaller K than 0.10? How many vote bigger? How many vote smaller? How many didn't vote? 8 trillion points off for tomorrow's exam. Or put another way, for you folks that didn't vote, I'll expand the exam to 2,000 questions. You get 10 minutes. And unless you make 80% or better, you flunk. I'm a rotten bastard, aren't I? Notice that. I'm treating silver oxide with ammonium ion, pardon me. What reaction will happen first? The ammonium ion will protonate oxide ion. And in so doing, make what? Ammonia and? You're not going to make any hydroxide ion in the presence of excess this. Water, you betcha. And these ammonia molecules, after they're formed by this reaction, will then do what? Will they react with silver ion as the silver oxide dissolves and make the silver ammonia complex ion? You're daggone right. So we can start with this. Now comes one more $64 question. By the reaction of silver oxide with ammonium ion, and I'll give you all the ammonium ion you want, is it possible to complex all the dissolved silver ion? By treating silver oxide with ammonium ion. That's what this is about. Is it possible for all the silver ion that goes into the system to be complexed and wind up as the silver ammonia complex ion? Or must some silver ion from dissolved silver oxide wind up in the system silver simply as the silver ion AQ? Yes. Absolutely. Why is that true? Mole of silver oxide is going to consume 2 moles of ammonium ion, no more. That will make us how many moles of ammonia? How many moles of ammonia? I'm only deprotonating 2 moles of ammonium ion. So this will give me 2 moles of ammonia, which means how many moles of silver ion can I complex? 1, but there's 2 moles of silver ion in silver oxide. So beside this, I'll also get this. But K is bigger. K is bigger because for this system, I not only have a better acid-base attack than I had here. Here, water, much weaker acid than ammonium ion. as a consequence of this acid attack on oxide ion, I'm making ammonia which can form silver ammonia complex ion. Let's see if I got that here someplace. Probably do. There it is. K went up to 18. And so I should think the last question here, what if I treat the silver oxide with a ammonium ion buffer? What kind of K value am I going to get relative to 18? If I treat silver oxide with a system that's rich in ammonium ion and also rich in ammonia, a much bigger K, because now I'm ready to beat the hell out of oxide ion, and I don't have to manufacture ammonia molecules to complex the silver ion. The system is already laced with ammonia, right? I put them in there. So if I do this, I'm going to get a much bigger K for this last system. K for this last system, I don't know, I got it here someplace. See if I can find it at a glance. Aha! 1.8 times 10 to the fourth. Woo-hoo, K went up a lot. You can answer all this if you just pay attention to the chemistry of the system. You can answer all this without calculation at all. So with that, let's offer a couple comments on section 19.5. Because what you have done so far to date, among many things, is to learn a lot about chemistry, a lot of different chemistry we've considered. And the simplest and best way to describe the chemistry of a system is to do what? Write the correct equation or equations for the reactions that occur in the system. Okay? So, rather than pay attention to the stuff that you see in the notes on section 19.5 amongst the questions, let's go to section 19.5 and take a look at what you see at the top of page 1924. We're going to relate that to something which you did or were asked to consider yesterday. Conversion of calcium carbonate to calcium sulfate. And one of the considerations you made was to treat calcium carbonate with ammonium sulfate solution. So you had ammonium ion to attack carbonate ion and sulfate ion to attack calcium ion. A double attack, like the double attack that we have here in dissolving silver oxide. When you treat it with ammonium ion, because that makes ammonia, that gives you the attack on silver ion. Or the immediate double attack with the ammonium ion buffer, where you got ammonium ion to attack oxide ion and the ammonia to grab the silver ions. So here's a double attack. This attacks carbonate, this attacks calcium ion. All right? Well, this K you've already looked at. You did this yesterday in discussion class. You get 7.9 times 10 to minus 3, which tells you this is not a very effective way to convert calcium carbonate to calcium sulfate. But what if I took this system and bubbled CO2 gas through it? What impact would that have on the effectiveness of this conversion? How would I affect conversion of calcium carbonate to calcium sulfate? If I take this system all by just as it stands there, and get me a tank of CO2 and bubble the CO2 through this system, will that have a positive impact on this conversion? Or a negative impact? Or no impact? Three possibilities exist. Positive, negative, zero impact. How many vote positive? Why do you vote positive? The CO2 added to water gives you hydrated CO2, doesn't it? Is hydrated CO2 a stronger acid than ammonium ion? And therefore, the more effectively I attack the carbonate ion with sulfate ion in the system, the better chance I have to cause calcium carbonate to become calcium sulfate. That's correct. If I do this, I'll get K equals 5.9. How will I rewrite the equilibrium reaction? What will I do to this equilibrium reaction as it stands to turn it into the equilibrium reaction for which K is equal to 5.9? Well, I'm going to take this out of there. Why am I going to take this out? Because the CO2 in water is a stronger acid. I'll just do this straight away. I'll imagine keeping the system closed so the CO2 bubble lid will stay in solution. And convert 2 moles of reactant water to 3 moles of reactant water. Why did I do that? That's right, because the CO2  1 mole and the 1 mole extra of H2O gives me this stuff. All taken care of by just doing what I did. What will I change product-wise? Well, I got to take this out. Well, let's do it. Because when H2CO3 reacts with carbonate, I get 2 moles of bicarb, right? And that's it.
I mean, the reaction errors are on the...
Well, I put this over here. Okay. That make you happy now? Good. One more question. Probably the simplest of those which I have so far asked. What will happen to this system if I add, so all this stuff, what happens now if add, say, 1 molar acetic acid solution? Will the conversion now even be better?
Yeah.
Is acetic acid a stronger acid than hydrated CO2?
Yeah.
You betcha. Now 1 more. What if I add 1 molar HF? Does that make this conversion better? It absolutely does not. Why not? Because if I hit this with HF, I'm going to make calcium fluoride. I'm not going to make any calcium sulfate anymore. Because calcium fluoride is a lot less soluble and more stable than calcium sulfate. Don't ever forget the inventory and the information that you have got to use that's on the information sheet.